So now let's talk about the other temperature extreme. Let's talk about cold temperatures. Now, when we go to colder temperatures, we are decreasing the motion of the molecules, so there's going to be even less chance for decomposition. So we don't worry about chemical decomposition so much at cold temperatures. What we are concerned about is physical changes to the liquid, and in particular, the liquid freezing or precipitating settleable solids. Now, one of the best tools that we have for understanding the low temperature storage characteristics of liquids is the freezing point curve. Many customers request freezing point curves for commercial liquid de-icer products, and so most commercial liquid de-icers are going to have them available for you. You can just ask for them. Now, even though they're very commonly asked for, they're often frequently misunderstood. People will often try and use the freezing point curve to determine the lowest effective de-icing temperature of a particular liquid, or to determine what concentration it will melt ice best in. Turns out they do not work very well for this purpose for a variety of reasons. And we can talk about that in a future one of these sessions. But for the moment, just let me give you a brief synopsis of what they are useful for, which is understanding the low temperature storage characteristics. So let's take a look at an example. What you see here is a freezing point curve for liquid sodium chloride, for plain salt brine. And what this curve is showing us is how the freezing point of the brine changes with the concentration of the salt. So let's just go from left to right over this graph. Now, starting way on the left side, at 0% sodium chloride, of course we just got pure water. We know water freezes at 32 degrees Fahrenheit. Now, as we start moving to the right, we dissolve more and more salt in my brine. And note that as we do that, my freezing point steadily drops. Now, why is the freezing point dropping? In simple terms, we can think of it this way. As I dissolve salt in my water, in fact, if I dissolve anything in water, it doesn't matter what it is, essentially what we're doing is introducing foreign particles. We're introducing molecules that are different from the water molecules, and they'll get in the way of the water molecules, and they'll make it harder for the water molecules to come together, find each other so they can freeze. That's a little bit of an oversimplified explanation, but it gives you the gist of what's going on. So the more salt we can dissolve, the farther we're going to drive down the freezing point. So notice that as we keep moving to the right, the freezing point gets lower and lower and lower until it bottoms out. We run into a brick wall at about 23% sodium chloride. At that point, the freezing point's not going to go any lower. It's what we call the eutectic. The eutectic is the lowest freezing point that you can get when I dissolve a given chemical in water. Now, why do we run into a brick wall? Well, the reason is, again, because it's the salt that's driving down the freezing point. But there's a limit to how much salt I can dissolve in water. I can't keep dissolving salt infinitely. At some point, that water is going to be holding all that it can hold, and it's going to be saturated. So that's what's happening at the eutectic. The water is holding all the salt it can. And the only way I can get more salt to dissolve is if I raise the temperature. So that's what happens when we move to the right of the eutectic. As we keep going to the right, now we can dissolve more salt, but we pay a price for that by having a higher freezing point for the brine. So now let's look all the way to the right at about 26% sodium chloride. That is saturated brine at room temperature. Now, note that at 26% sodium chloride, the freezing point, quote unquote, of the brine is about 32 degrees Fahrenheit. Now, what that means is that that brine is so full of salt that if I cool it down, the very first thing that's going to happen is it's going to salt out. That is, it's going to become super saturated in salt. It's not going to be able to hold it anymore. And that excess salt is just going to come crashing out of the brine and settle to the bottom of the tank as salt crystals. Now, we want to avoid either one of those from a storage standpoint. If we have a brine composition that's on the left side of my eutectic and I get too cold, it's going to freeze. It's going to form ice crystals, and I'm going to have slush. And that slush is not going to pump or flow well. On the right side of my eutectic, if it's too concentrated, I'm going to salt out and get salt crystals falling into my tank, and it's going to clog spray nozzles and clog lines, and we're not going to want that either. So the freezing point curve tells me what concentrations of my liquid are going to be stable at a given temperature range. We want to make sure that we're looking at the freezing point curve for the particular liquid that we have. Now what you see here is a series of freezing point curves for a number of common de-icing chemicals. And note that they're all different. They've all got different eutectics, different minimum freezing points. These particular graphs are all for the pure chemical in water. And something to be aware of is that when you buy a commercial liquid, they're often going to have other additives in them, maybe performance enhancing additives, or there might be impurities present in them, and these can affect the shape of that freezing point curve. So for example, magnesium chloride. Magnesium chloride liquids will sometimes contain sulfates as impurities. And the sulfates will crystallize out at a warmer temperature than plain magnesium chloride will. So the bottom line is just you want to make sure that you're looking at the freezing point curve for the actual liquid that you're buying. And you can usually request these from the manufacturer. Now, one other bit of information that's useful in understanding how your liquid is going to behave at cold temperature is results of settlable solids tests. Now, there is a settlable solid standard that was developed by the Pacific Northwest Snow Fighters, or the PNS. It's based on a fairly simple test. You take a 1 liter cone, you fill it up with a liter of the liquid, and you store it at a characteristic cold temperature that's set for that chemical. It's going to be lower for calcium chloride than it is for plain salt brine, because calcium chloride will store at a much colder temperature than salt brine. You store it there for a week. That gives it enough time for any solids that are going to form to drop out of the brine and settle to the bottom of the cone, and therefore we can measure the volume of the solids. And the typical PNS specification is that liquid de-icers should contain less than 1% settlable solids at that particular cold storage temperature. And so most commercial liquids you buy will probably be formulated to be stable to this extent, down to the quote-unquote typical cold storage temperature. So that will give you a good guideline of what to expect in terms of how much solids you might get if it gets stored cold. And if you want to know what happens if it gets stored outside of that range, you could always run a similar kind of test or request that kind of data from the manufacturer.